All right. Good morning once again. As we uh, continue with our study on factors affecting equilibrium. All right. So yesterday in our lecture, we looked at the effects of concentrations, on equilibrium, on the position of equilibrium. When you add maybe a reactant, how would the equilibrium respond? Of course, it will respond in a way to consume the reactant added. That means that it will favor the formation of the product. If you removed a reactant, then equilibrium will respond in such a way as to generate more of such reactant. So it will shift to the left, favoring reactant. If you had a product, the equilibrium will respond in such a way as to consume the added amount of product. All right, so the direction that consume product is the reverse direction. So increasing any of the products, we shift equilibrium to the left, decreasing the formation of the product, and of course, decreasing any of the products is as the product being formed, it's being removed. Then of course the equilibrium will shift in the direction that produce more of such products, and that's what is displayed here with this example: PCl3 plus Cl2 to give us PCl3. Increasing PCl3, okay, will cause a decrease in the amount of PCl3. The same thing with Cl2 because they are reactant. Okay, so I think this illustration is explicit enough for anybody to comprehend. All right, so let's now look at another important factor. And at this point, I will be glad if you can just listen carefully because in this one involves a bit of thinking. Now, we're looking at effect of change of volume, change in pressure, or addition of inert gas on equilibrium and product formation. For gas phase reactions, the change in volume or pressure or inert gases will affect the position of equilibrium. But for reactions, for example, in an heterogeneous equilibrium, where you have at least one of the species involved at equilibrium be in a different phase, it could be solid or liquid, the change in volume or change in pressure will not affect such species. And so if it's, for example, let's look at the decomposition of calcium carbonate. All right, calcium carbonate is solid. One of the products is calcium oxide, is solid, and of course the other product is carbon 4 oxide. It's only the carbon 4 oxide, which is of course the product, that could be affected by change in volume or change in pressure or addition of inert gases. But for an homogeneous equilibrium that does not involve any gas at all, then the change in volume or pressure does not affect such a process. Or I think we should have that registered in our mind. Having said that, now for gas phase equilibrium, the most important thing to look at when you are considering the effect of change in volume or pressure is to look at the number of moles of gaseous reactant and of course gaseous product. If the total number of gaseous reactant is equal to the total number of gaseous products, then change in pressure or volume will not have any effect on such equilibrium. For example, the reaction of hydrogen plus iodine, H2 plus Hi2 to give 2Hi, all in the gaseous phase. The product, 2Hi, 2 moles of hydrogen iodide in the gaseous state. And on the reactant side, we have 1 mole of hydrogen and 1 mole of iodine, making the total number of moles of 2, also on the reactant side. So that delta N, the change in number of moles, which of course is defined as the number of gaseous products minus number of gaseous reactant, will be equal to 2 minus 2, which will be equal to 0. For such a reaction, change in pressure or change in volume or addition of inert gas has no effect whatsoever on the position of equilibrium. All right, so that is number one. Number two, when the change in number of moles is positive, now what that means is that you have more gaseous products than you have gaseous reactant. You have more gaseous products than we have gaseous reactant. Under that condition, under such condition, if the gases are assumed to be behaving ideally, if the gases are assumed to be behaving ideally, then taking ideal gas equation to consideration, PV is equal to nRT, which means that P is equal to nRT over V. It means, therefore, that P is proportional to number of moles. So how does the effect of change in pressure affect such a system at equilibrium? Now let's look at this, what we have. Okay, sorry, I've moved the slide to the next. Let me go to the previous slide. All right, so when delta N is positive, it means that you have more of the gaseous product than you have gaseous reactant. So if there is an increase in pressure, you are invariably increasing the number of moles. And the side that is affected by that increased number of moles is the side that has more number of moles, since pressure is proportional to number of moles. All right. So, for example, in the illustration given above, we're looking at PCl. Let's look at it together. I think I have it here. All right. So we have this illustration here. PCl5 decomposing to give PCl3 plus Cl2. You have 2 moles of product and 1 mole of reactant. So delta N is positive. If you increase the pressure, you are invariably increasing the amount of products. That's the implication, because you are increasing the number of moles, and the direction that has more number of moles is the product side. So how then will the equilibrium respond as to annul the effect of this increase in pressure, which corresponds to increase in number of moles, is to shift in the direction that consume more moles. And the direction that consume more moles is the reverse reaction. So therefore, for a PCl5, PCl3, Cl2 equilibrium, increase in pressure will shift equilibrium to the left. That is that is to say, the composition of PCl5 is reduced, is disfavored, because PCl5 is produced. Instead of it being decomposing, more of it is being produced. Okay, that's how the change in number of the amount of pressure, sorry, the increase in pressure will affect such a process. Now, what happened to decrease in pressure? If there's a decrease in pressure, you are invariably decreasing the total number of moles. The direction that will be affected most is the direction that has less number of moles. All right, for example, in this illustration displayed, if there's a decrease in pressure, then it means that you are decreasing the PCl5 concentration. Okay, and so the way the equilibrium we respond to that is to shift equilibrium to the direction that produce more of PCl5. Okay, sorry, please. Let me recap that again. If you decrease the pressure, you are invariably affecting direction that has more number of moles, and that is the product side. That's the product side. So therefore, decrease in pressure will then shift equilibrium to the right. That is, will lead to more decomposition of PCl5. Okay. I hope that is taken. All right. Now, the reverse of what happened when you change pressure is what will happen when you change volume, because according to Boyle's law, pressure is inversely proportional to volume. Pressure is inversely proportional to volume. So let's look at this illustration again. If there's an increase in volume, If there's an increase in volume for the PCl5, PCl3, CL2, no, it's not PCl2, please. This should be Cl2. Okay, please note that what you have here is not PCl. There's no PCl2 because this is not balanced. You only have one mole. We only have one phosphorus, so this should be Cl2, please. Where you have PCl2, please remove it and change to Cl2. All right. I haven't done that. Now let me go back now to what happened to a change in volume. If there's an increase in volume, you have invariably decreased the pressure. And by decreasing the pressure, you have invariably decreased the direction that has more number of moles. All right. And so therefore, increasing volume favor the decomposition of phosphorus pentachloride. That is, it will favor product formation. And of course, decreasing the volume will shift the equilibrium to the left, favoring the formation of PCl5. Okay, so that's how the change in volume and pressure affects this system at equilibrium. Now, what happens if an inert gas, that's a gas that does not react or is not involved in the reaction, is added to the system? Okay, there are two things the presence of inert gas could do. The presence of inert gas could either increase the pressure or increase the volume. Okay, if an inert gas is added and the pressure is held constant, the pressure at constant pressure, and inert gas is added, what the inert gas will do is to cause a change in that pressure by increasing the pressure. And if pressure is increased, the only way the equilibrium will respond is to consume more number of moles. Therefore, addition of inert gas to a system display above will favor the formation of PCl5. That is, it will shift equilibrium to the left because that's the direction that consumes more number of moles. All right. If the reason for adding an inert gas is to cause an increase in volume, initially the volume will be constant, but when you now add an inert gas to the system, there'll be an increase in volume. And what's the meaning of increase in volume? It means that there will be decrease in pressure. And if there's a decrease in pressure, then the direction that has more number of moles will be affected more. And so therefore, equilibrium will shift to the right. It will shift to the right, favoring the formation of chlorine and PCl3 and decreasing the PCl5 formation. Okay, so that's how the presence of inert volume will affect a system where delta N is positive. Now, what happens when delta N is negative? What happens when delta N is negative? For example, in the formation of ammonia, nitrogen 1 mole, hydrogen 3 moles, ammonia 2 moles, such that delta N is -2 because we have 1 mole of nitrogen, 3 moles of hydrogen, that's 4, 2 moles of ammonia, that is 2, and delta N will be equals to the number of moles of product minus number of moles of reactant, that will be equals to 2 minus 4, which will be equals to -2. So a very good example of such system is the formation of ammonia. What happens if there is an increase in pressure? There's an increase in pressure, the amount of reactant will increase because you have 4 moles of reactant and 2 moles of products. So if you increase the pressure, it will affect the amount of reactant more than the amount of product. And so the only way the equilibrium will respond as to annul the effect of this increase in pressure is to favor formation of ammonia. So if you're an industrialist or after you have graduated from the university, you want to be an industrialist producing ammonia as a feedstock for fertilizer formation or production, or you are lucky to get a job at Dangote Fertilizer, okay, where urea and the likes are being produced. And of course, as a chemist or a chemical engineer, you may be asked, what should be done to increase the yield of ammonia? All you need to tell them is that to increase the yield of ammonia, please increase the pressure. If you increase the pressure, there will be increase in the formation of ammonia. Okay, that is about increase in pressure. Now, what happened? Okay, that's what I said here. Increase in pressure or decrease in volume will increase the formation of the product. Okay, I've just explained that now. What then happens if an inert gas is added? Like I said in the previous slide, the essence of adding inert gas could be to increase pressure or to increase volume. Now, before you increase pressure, the system will be at a particular pressure, a constant pressure. So if you now add an inert gas, the inert gas will cause an increase in the pressure of the system. And so therefore, it will then lead to formation of the product because you have increased the pressure. And of course, that means that the volume is decreased. So, I mean, whether it is increase in volume or decrease in pressure, they go hand in hand. So that is that about the effect of change in pressure and volume for a system where delta N is negative. I hope that is that should be clear for all of us to understand. All right. Before we continue, however, let's take our first attendance code for today. The first attendance code is C4DMM. 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 Okay. Please, let's write that down. Let's go to the attendance page. C4DMM. Christ for Dio. Maybe I should use that one. Christ for Dio. That is Christ for Dio. Munirat and Mary. Okay? Christ for Dio, Munirat, Mary. C4DMM. All right. So let's take that as our attendance for the first attendance for today. Okay, let's make progress. Now, of all the factors that could affect equilibrium position, the only one that will affect equilibrium constant, as of course it will affect equilibrium position, but the only one that will affect the magnitude of equilibrium constant is temperature. So let's see how will change in temperature affect the position of affect equilibrium and of course product formation. Now, a reaction can be classified as either exothermic or endothermic. Now, a reaction is exothermic when heat is lost. In one word, for an exothermic reaction, heat is part of the product. One word, for an exothermic reaction. However, for an endothermic reaction, it's a reaction that involves gaining of heat, absorption of heat. So in one word, heat is part of the reactant. Okay, or energy is part of the reactant for an endothermic reaction. And that is what I've illustrated here. Now, the question is, how does the uh, increase in temperature affects an exothermic equilibrium. By increasing temperature, you are increasing the product because heat is part of the product. And if you increase temperature, you are increasing energy. And since energy is part of the product, the only way the equilibrium will respond is to consume energy. And the direction that consumes energy is the reverse reaction. So therefore, increase in temperature will decrease the product formation. That is, we increase the reactant formation and decrease the product formation. And if there's a decrease in temperature, then that means that you have decreased the energy that is part of the products. And the only way the equilibrium will respond to annul this effect is to produce more energy. And so the direction that produces more energy is the forward direction. So therefore, decrease in temperature will favor product formation. That's for an exothermic process. For an endothermic process, since energy is part of the reactant, increase in pressure we favor the direction that consumes energy, and that is the product formation. So therefore, when there's an increase in temperature for an endothermic process, the equilibrium will shift to the right, favoring product formation. And of course, decrease in temperature will mean that the energy has decreased, and the only way the energy can be brought back to what it was before is to favor the direction that produces energy, that is favoring reverse reaction. So decrease in temperature will decrease product formation and favor reactant formation. So back again to our EBA process. The EBA process is an exothermic process. It's an exothermic process. Okay, because it's exothermic, so it has to be carried out at low temperature. It has to be carried out at reduced temperature because that's the condition that favor formation of products. Okay. Oh, beautiful. Okay, so increase in temperature for the EBA process. Now, before I explain this, let it be known that if the forward reaction is exothermic, then the reverse reaction must be endothermic. If the forward reaction is exothermic, then of course the reverse reaction will be endothermic. All right, so if there's an increase in temperature, then this will prefer an endothermic reaction, okay, because it takes energy. In one word, increase in temperature will not favor exothermic process, okay, because in that process, energy will be consumed. There'll be a decrease in energy, okay? So an endothermic reaction is a reverse reaction, and it is favored. So the yield of products will be of ammonia will decrease. However, if there's a decrease in temperature, of course, the equilibrium will shift in a direction that produces more energy, and that favors exothermic reaction, favoring the yield of ammonia. Right. And like I said, of all the constraints considered so far, the only one that will affect the magnitude of the equilibrium constant is temperature. However, the quantitative description of the effect of temperature on equilibrium is beyond the scope of this course. And that's why we are not doing anything quantitative here. Okay. When you get to, for my students in biochemistry, chemistry, industrial chemistry, geology, microbiology, and when you get to your second year, when you'll be doing physical chemistry 1, then of course, we may have to teach you the if the effects or the quantitative effect of temperature on equilibrium. But until then, let us be happy with this qualitative description. All right, another factor worth considering is the effect of catalyst. Effect of catalyst. Does a presence of a catalyst has any effect at all on the position of equilibrium? We shall see. Question first is, what's a catalyst? A catalyst is any substance that changes the rate of the reaction. It could increase it or decrease it without quantitatively taking part in the reaction. That is, a catalyst is, is a substance that is added that will affect the rate of the reaction without itself being consumed. Okay. Now, so we can have a positive catalyst, the one that causes increase in rate of reaction, or we have a negative catalyst, which we call an inhibitor. An inhibitor is the one that causes a decrease in the rate of the reaction. Now, for a reversible reaction, the change of reaction rate is same for both forward and backward reaction. Okay, and the ratio of the reaction rate remains the same, which we call the equilibrium constant. And so the equilibrium constant, which is the ratio of the rate constant. Okay, so the presence of a catalyst may speed up or delay the attainment of equilibrium, but it will never affect equilibrium concentration. And since equilibrium concentration is not affected, the presence of a catalyst has no effect whatsoever on the position of equilibrium. It can only delay or speed up the attainment of equilibrium, but not the position of equilibrium. Okay? And I think with this, we will have come to the end of our discussion on factors affecting equilibrium position. Factor affecting equilibrium position. All right, let me hear you. If you have any challenge. Yes, C4DMM. Thank you very much. I think the class is very few. We have about close to 6,000 students that register for this course, and today we have just 1,899 students that are present in class today. All right, so you can see if we have we are just about 25% of the students in class. So we pray that you all do well in Chemistry 101 exam and test that is forthcoming. But of course, if for any reason the performance is not good enough, it will be a reflection of your involvement in the class. Definitely, it's going to be a reflection of the involvement of students, because, like I said, we're expecting close to 6,000 students in the class for every class, and here we are having just 1,945 as at this moment. Okay, so you're not going to, because I'm sure you are in your first year, and of course you must have been a lot of things must have been said about White House. Oh, White House, they make life difficult for students. We don't make life difficult for students, but of course you can see yourself that you've not been actively involved in the class. You've not been actively involved in the class. Somebody's asking, can we come to your office if you get question? It's okay. You can come, but let it be between 1 and 3. Anything beyond that, please don't come to my office. But of course, the door to my office always open between 1 and 3. Yeah, this is secondary school work. I know you've been taught in secondary school. Okay, can I explain the effect of pressure? Okay, Meleki Mayawa, just listen to me. I'll try now. Please listen to me. The effect of pressure. Now listen, before we discuss effect of pressure, you need to first look at the equilibrium, so the stoichiometry of the reaction. If you have more gaseous products than you have gaseous reactant, we say delta N is positive. And so therefore, increase in pressure will invariably cause an increase in the number of moles of the product more than the reactant. And that's a stress. And the only way the equilibrium will respond is to consume more of the product. So therefore, for a system where delta N is positive, increase in pressure will decrease the formation of products. That is, it will shift equilibrium to the left. It will shift equilibrium to the direction that has less number of moles, which of course will be the reactant side. Okay? That is how the pressure will affect the equilibrium position for a system where delta N is positive. Now, when delta N is negative, it means that you have more reactant than you have products. So increase in pressure, therefore, will increase the reactant more than the product, because pressure is proportional to number of moles. And so therefore, increase in pressure will shift equilibrium to the right, favoring product formation for a system where delta N is negative. The converse of that, or is what will happen when you have increase in volume or decrease in volume, since pressure and volume are inversely proportional. Okay, so I hope that is understandable to you. Meleki Mayowa, all right. How Q affects K, all right. Q is called reaction quotient. For any reaction, whether it is reversible or irreversible, the reaction quotient is simply the ratio of the product of the concentrations of the products to the product of the concentrations of the reactant raised to their stoichiometric coefficient, as long as they are elementary reactions. Okay, that is Q. Q will be equals to K when the system is at equilibrium. Q will be equals to K when the system is at equilibrium. Am I communicating, please? All right. Now, Q will be greater than K when you have more products than you have reactant. In one word, you have increased any of the products, then Q will be greater than Kc. And the only way the equilibrium will respond is to consume more of the products, so that Q now become K. All right. So that's how Q and K are related. Okay. Somebody said increase in pressure will shift the equilibrium to the side with lower molar concentration. Well, it's no molar concentration, because we're not talking about ionic as solutions here now. We're talking about we shift the equilibrium to the direction with lower number of moles, not molar concentration. Or Tesaya, or lower kime, or whatever. Okay? So increase in pressure will shift the equilibrium to the side with lower number of moles. All right. So thank you very much. Now, as we continue, let's look at the second code for today. The second code for today is BW5YJ. BW5YJ. Bidemi Wosilat 5. Jemi Jonathan. Bidemi Wosilat 5. Jemi Jonathan. Bidemi Wosilat 5. Jemi Jonathan. BW5YJ. Okay, what happens when Kc is equals to Kp? Beautiful question. I like that. Kc will be equals to Kp when delta N is equal to 0. Kp will be equals to Kc when delta N is equal to 0. Because Kp is equals to Kc multiplied by RT raised to power delta N. And if delta N is equal to 0, then RT raised to power delta N will be equals to 1. And then Kp will be equals to Kc. All right. Is Bideni Wosilat 5? Yemi Jonathan, not G-O. I said Jonathan. J, not G. Ifeoluwa Awonuga, please, is J and not G. Please don't confuse your colleagues. So, okay, thank you very much. Aha, thank you. Awonuga, you have seen it. That's very good. That's very good. All right. Any other question? So what are you trying to say if I missed? Okay. Somebody say, so what you are trying to say, if I'm mistaken, is that when delta M, it's not delta M, it's delta N. N, not M. N. Delta N. I didn't say M. Adebowale Tobi, please, it's delta N. Okay, so when delta N is positive, increase in pressure will shift equilibrium to the left. Okay. Yeah, this video is available to watch on YouTube. You are correct. Please. Somebody is still asking for force code. You are still asking for force code. C4DMM. C4DMM. That's the force code. All right. Yes. The mole ratio for EBA process has more moles on the reactant side. That's true. Melekimaewa, you have 4 moles. That's delta N is negative, not positive. Delta N is negative, not positive. So increase in pressure will favor ammonia formation. Okay? Increase in pressure for the EBA process will favor ammonia formation. Because when you increase pressure, you are invariably increasing the reactant more than you are increasing the product. Because you have 4 moles on the reactant side, and of course 2 moles on the product side. So when you increase the pressure, you have increased the reactant more than you have increased the product. And so the only way the equilibrium will respond is to consume the reactant that you have you have increased its amount. Okay, so therefore it will favor the direction with lesser number of moles. For delta N is negative. All right. I hope that is understandable now. All right. Any other question? I'm enjoying your comments. Any other question? Will pressure affect Kp for gaseous medium, sir? Yes. Yes. Pressure will affect Kp. Of course, Kp is equilibrium constant measure in terms of partial pressure. Kp. So definitely Kp will be affected by change in pressure. I didn't know, easy boy. No. I didn't say, yes, pressure will not affect the magnitude of equilibrium constant, but it will affect the change, it will affect the position. Okay? You see, it will affect the position, it will affect the composition. There will be change in composition, but the equilibrium constant will still remain the same. Okay? The equilibrium constant will still remain the same, even though there will be change in composition. Some will increase and some will decrease. Eventually, you still have the same value of equilibrium constant. Okay? All right, effect of inert gases. Like I said, two possible things will the inert gas do. Is either to cause an increase in pressure or to cause an increase in volume. So if a system is at constant pressure, then it can cause an increase in volume. And if it causes an increase in volume, then it will favor the direction that has decrease in increase in volume is like decrease in pressure. Okay, so you have to first know what is the value of delta n, whether delta n is negative or positive. That's the first thing you need to first know before you begin to look at the effect of inert gases. Okay, so if, for example, for a situation where delta n is positive, and at constant pressure, you have added an inert gas, so you cause an increase in volume. And if delta n is positive, then it will favor product formation. That's increase in volume. But decrease in volume will favor reactant formation. Therefore, delta n is positive in the presence of an inert gas. Okay? I hope that is easy, boy. I've just explained the question, what you asked now. So literature principle is just for temperature, concentration, catalyst, and pressure. It does, in fact, the catalyst does not have any effect. Please. Okay, I just mentioned so that you don't get confused, because you'll be asked, what's the effect of catalyst on position of equilibrium? It has no effect whatsoever. The only thing catalyst could do is to speed up or decrease the rate of attainment of equilibrium, but doesn't affect equilibrium position or composition. Okay? The time duration for your test on Saturday, well, likely to be, you're going to have about 40 questions in the test, 40 questions. And it's going to be like 70 minutes. 70 minutes. 70 minutes. Not more than 70 minutes. It can't be more than 70 minutes. Max 70. Because there are multiple choice questions. There are some of the questions that if you have been studying over time, you've taken your time to study over time. There are some of the questions you just see, you pick your answer without any calculation, without thinking too far. There are some of the questions you just see and you pick your answer. Yes, stoichiometry, you have to do calculation. Okay, so it's only virtually or most questions stoichiometry we have to do a calculation. Okay, for equilibrium, it's going to be a mixture of calculation and non-calculation. It's a test of understanding. Okay, while for the first two topics, the introductory parts, the gas law, and of course, you're not going to talk about gas law without talking about calculation. So definitely there'll be some calculations and there'll be some intuitive learning. You just see it and say, okay, this is what's likely to be, and you pick your answer. Okay, and of course, for atomic theory, there is actually no calculation. There may not be any calculation, rather, let me put out, there may not be any calculation in atomic theory. Okay, since it's more of a qualitative, it's more of a descriptive study. Okay, but don't rule it out. There may be, okay, because apparently you are taught stuff like charge to mass ratio. Okay, you're taught charge to mass ratio. Okay, so if you know the charge, you can know the mass, and so on and so forth. You also taught the Broglie hypothesis, where you have momentum being inversely proportional to wavelength. So there could be some questions, or I don't know, but I'm only imagining what are the likely. So if there's going to be any calculation at all in the topic, these are the areas you may want to look at. Except for that, I don't think. Then of course maybe you want to look at you want to look at line emissions spectrum, okay, all this delta E is equals to delta E is equals to what's it now? H no, okay, H no, okay, that's Planck constant and frequency relating to energy. Okay, if there is any, okay, that's likely the area you may see few calculation, if there's any. All right, the last code, thank you. The last code for today. The last code for today is Shalewa 4 X-ray Ebenezer 2. 4 S4 X E2. Shalewa S for Shalewa 4, figure 4. X-ray, xylophone, okay, X. E Ebenezer, then 2, figure 2. So it's S4 XE2. X, thank you very much. Night design, yes. X S4, good. XE2, thank you very much. X4 S as in Shalewa, please. S4 XE2. Okay. Yeah, it's CBT. Adizamiri is CBT. Yeah, CBT. Okay. So what I'm going to do, because I'm going to be here again tomorrow, I'm going to take time to listen to your questions. So as many questions as you have, I hope that I will be able to solve out the problem of writing. My challenge is this thing is not right. I don't know what went wrong since we resumed. If I'm able to solve it, I hope to tomorrow, before tomorrow rather, so that we can then, if you have any question, feel free. Then I will try today to set up a personal Google classroom, okay, so I can post the slides. I can post the slide on the Google Classroom. I would have loved to use OAU, but you have not been given students' mail, so you might not be able to access that. But I will open on my Gmail today and post, so I can give you the code so that I can access the notes. Hopefully, by the grace of God, tomorrow I'll do that today. All right. So thank you very much. The link to submit attendance is not opening. Are you sure? Abosede, are you sure? Check it again. No? Can we bring in scientific calculator? Oh, sure. We're in the university here. Bring your calculator, please. Bring your calculator. But if you bring Orijo in your calculator, we will catch you. And if you are caught, in your first test ever, I'm sorry, that may be your end in this university. So you don't want to go that way. Please don't go that way. Don't go the direction of fraud. Study, okay? All right, so I will still see you tomorrow, 8 o'clock tomorrow. Don't worry, we'll talk more. All right, till then, have a great day. God bless you. All right. This house, so tomorrow will be education. The problem with this thing is because it's free, but it's locked. Okay, because it's doing. The light is exactly. So they want to get the paid version. So I don't even know how much the paid version is. That paid version is around 10,000. I pay for it.